Hello, nice to see you. Good afternoon.
Good afternoon, Professor.
Good afternoon. Nice to see you guys.
Good afternoon.
Hi. So, as I mentioned last time, we are going to start new topic today that will be electromagnetic field, electromagnetic waves. And we will try to find the relationship between all sources of magnetic and electric fields. So we will first introduce such concept as displacement current, Maxwell displacement current, and then we will make a transition to a consideration of all four Maxwell equations, which together with Lorentz equation, which describes at every moment of time the total force, like electric and magnetic force acting on the charged particle. All together, they provide full description of electromagnetism. And based on that, our first step will be to derive expression for the speed of light, and we will show that speed of spreading electromagnetic wave in free space, in vacuum, where we don't have any current and any electric charges, will be equal to speed of light, which experimentally measured, and they coincide, meaning that visible light is also a form of electromagnetic wave, and proves that all these Maxwell equations are applicable to visible light in the same way as for lower frequency electromagnetic waves, some radio waves, and microwaves. Okay, so now let me switch to our slides. And let us recall Amperes Law, which we discussed not so long ago. So the integral over a closed path of B vector times ds vector, which magnetic field vector, times displacement vector, is equal to mu naught times I, electric current. What does it mean? So in general, if we have some conductor and there is some electric current I flowing through the conductor, so if we consider some closed path and take this integral along the closed path, its value should be equal to the product of permittivity, magnetic permittivity of free space, times electric current, which flows through the surface determined by this closed path. So that is Amperes law. And also we need to remind that electric current is the rate of change of electric charge. So it's first derivative of electric charge over time. Now, let me share with you my screen. Let's take a look at this image, like this sketch. So we have a conductor and capacitor. So some wire attached to two plates, which represent some parallel plate capacitor, and there is some AC alternating current flowing through the this component of an electric circuit. So now let us consider one path, so these dashed black lines, but two surfaces associated with this dashed closed path. First surface will be this bluish S1, and second surface S2, this yellowish surface. So if we consider Amperes law applied for path P, this path closed path which we agreed to consider in this case, then integral over this closed path should be of this product B vector displacement vector, should give us the product of mu naught and electric current I, which goes through this blue surface S1. So that is fine. Now we can use the same closed path, but consider this surface S2. In this case, integral over the same closed path actually will be equal to 0, because in the right side of Amperes law, we need current, like I, which is conductivity current, which is associated literally with charge transport in space. And here in this gap between two plates of the capacitor, we don't have any charge transfer in space, because this gap between two plates is an insulator. So taking this into account, the conductivity current I in the right side of this Amperes law should be equal to 0, and then integral over closed path P of B vector times ds vector should be equal to 0, which provides some discrepancy, because we use the same closed path. However, considering two surfaces associated with the same closed path, we get totally different results. And it provides some discontinuity of electric current, which should not be the case. So in order to solve this discrepancy, Maxwell proposed a concept of so-called displacement current. So nowadays it's called Maxwell displacement current. Let me come back to our slides. So he proposed that ID, displacement current, is equal to epsilon naught times dF E over dt. So with this, we can kind of write the general case for Amperes law. But first of all, let us highlight that this Fe is the flux of electric field. So we remember from previous discussions, Fe is equal to integral of scalar product electric field times dA vector. So if we have uniform field, so it's just product of electric field multiplied by area of the surface through which we determine the electric field flux, assuming that electric field is going perpendicularly to the surface of this area. In general case, we need to take integral of this scalar product of two vectors. So what does this mean, this displacement current? So here we have change of electric field flux over time, and that is associated with some electric current. So when we charge, so this capacitor, so we have this wire, then let's say we have our capacitor. So when we have some conductivity current flowing through the wire, it means that we either charge or discharge this capacitor. Depends on initial polarity and direction of electric current. So charging and discharging capacitor means that we change the surface density of electric charge accumulated at the plates of this capacitor. And we know that this will define electric field inside the capacitor. So here inside the capacitor, we have electric field, which will be related to this surface density. If we, because of conductivity current, change the surface density, we change electric field. If we change electric field, obviously we will change the electric field flux. And this changing over time electric field flux is considered as the source of this Maxwell displacement current. So now let us consider specifically a parallel plate capacitor, and let us show that they are really equal to each other. Means displacement current should be equal to conductivity current. So inside the parallel plate capacitor, we know that electric field is equal to surface density sigma of electric charge divided by epsilon naught, assuming that we have vacuum in between the plates. This we can write as total charge Q divided by epsilon naught divided by area of the plates. So electric field flux will be equal to electric field times area of the plates. Electric field here is constant because electric field between parallel plate inside parallel plate capacitor is constant, doesn't change with position, and that's why we can use this product, electric field times area. And considering expression for electric field, so we can substitute it here, we will get that it's equal to Q, electric charge accumulated, in the capacitor divided by epsilon naught. So area will cancel out. So now we, from definition of displacement current, it is equal to epsilon naught times d Fe over dt. So first derivative of electric field flux over time. That will be equal to epsilon naught times dq over dt, and here is 1 over epsilon naught. So these guys we cancel out. This will be dq over dt, and this is nothing else as our conductivity current. So we see that displacement and conductivity current, they are equal to each other. So now, taking all this into account, we can write more like generalized case of Amperes law, which will look as follows. So integral over a closed path of the scalar product B ds will be equal to mu naught, but instead of putting just current, which is conductivity current, we need to put now the sum of two currents, conductivity current plus displacement current. And to be more specific, it will look like mu naught times I, which stands for conductivity current, plus mu naught times epsilon naught times df e over dt. So that is the general case, which takes into account conductivity and displacement current. And this is important because so this general equation, like generalized Amperes law, is also called Amperes Maxwell law, obviously because we add to conductivity current also Maxwell displacement current. So in this case, we don't have any discrepancy, which we discussed at the beginning, because if we integrate assuming surface which goes through the closed path, and this surface goes through the conductor, like wire, which goes to the capacitor, then we deal with conductivity current. So when we consider surface which goes through the middle space between two plates of the capacitor, we consider displacement current. We have shown that both of them by magnitude are equal to each other. So doesn't matter which surface we consider, we will get the same magnitude of this integral over closed surface, closed path of a product B vector ds vector. Then everything works, and regardless of surfaces which we considered in this experiment. So what it means from practical point of view, it tells us that the source of magnetic field is not only conductivity current. So magnetic field can be created, we know this, by electric current which flows in a conductor, and we calculated this magnetic field. However, besides that, changing, like varying in time, magnetic field flux, which automatically means also varying in time electric field, can also serve as a source of magnetic field. And depends where we, in which part of the electric circuit, which we considered previously with this capacitor. Either we deal with the conductivity current or with associated with the change of magnetic of electric field flux, so-called Maxwell displacement current. But both of them, conductivity current and Maxwell displacement current, can be sources of magnetic field. So now let us consider 4 equations, which are called Maxwell equations. And also there will be one more equation for Lorentz force. So their combination provides full information about electromagnetic field. And this combination actually is called the system of Maxwell equations. So which equations we have here? So first, Maxwell equation will be integral over closed surface E vector times dA vector equal to Q divided by epsilon naught. So we will discuss later in details all of these equations again. Second equation is integral over closed surface B vector times dA vector equals to 0. Then equation number 3, integral over closed path of E vector times ds vector equal to minus df b over dt. And fourth equation, that's one which we actually discussed today and introduced additional component to go from Amperes to Amperes Maxwell equation, is integral over closed path B vector times ds vector equal to mu naught times I plus epsilon naught times mu naught times dfe over dt. Okay, so this is the so-called system of Maxwell equations. We have 4 equations. One more equation which we need to add here is so-called expression for Lorentz force law. Total force which is exerted on electric charge will be equal to Q times electric field vector plus this magnetic force. So we have 2 components, electric and magnetic force. It will be Q times V vector product with B vector. So this combination of 5 equations provide us all necessary information about any electromagnetic field and also its interaction with electric charge. So let's us go step by step through this 4 Maxwell equations. So any comments on equation 1? Does it tell you something? Have you ever seen this before? That's important equation which we considered long time ago. Probably that's why you cannot recall it. It was at the beginning of our course, and it is Gauss law for electric field flux. So electric field flux through any closed surface equals the net electric charge inside that surface divided by permittivity of free space epsilon naught, assuming that this is in vacuum when the electric constant is equal to unity. So the flux through closed surface is actually left side of equation 1, this one. And we know that regardless of the shape of this closed surface or any arbitrarily closed surface, electric field flux through this closed surface is equal to the net electric charge enclosed by this surface divided by epsilon naught. So this is all about electrostatic field created by electric charges. So we clearly can say that electric charge, regardless of its motion or stationary condition, is a source of electric field. And based on polarity, positive or negative, this electric field flux can be also positive and negative because that is related with the orientation of electric field lines with respect to the surface of this Gauss surface. So that is about first equation, and we keep this in mind. Electric charge is source of electric field. Now, equation number 2. This is the same, actually, Gauss law, but applied to magnetic field. So it tells us that magnetic field flux through any closed surface is equal to 0. Regardless of anything, it should be equal to 0. So based on this fact, we can claim that there are no magnetic so-called charges equivalents of electric charges, because these magnetic charges could be considered as some monopolies, monopole of south or southern or northern poles of magnetic of some magnet. They don't exist by themselves, just separately. They always exist in a pair. And that means that there is no origin or termination of magnetic field lines. They are uninterrupted. And that's why it doesn't matter what's going on. This integral, like in the equation 2, which calculates magnetic field flux through a closed surface, is always equal to 0. So there are no like equivalence of electric charges, which are sources for magnetic field. And that stands because we have here this 0. Now we proceed further. This is equation 3. And this equation, we discussed this equation not so long time ago, it was maybe a few weeks ago, which stands for Faraday's law. So it defines the relationship between electric field, induced electric field, and varying in time magnetic field, in particular here, varying in time magnetic field flux. So it tells that the integral over closed path of this product E vector ds vector, which is equal to induced electromotive force, is not equal to 0 if there is varying in time magnetic field flux. So in this case, we consider that this varying in time magnetic field flux is also a source of electric field, but not electrostatic field, but this induced electric field, which we considered in the scope of the Faraday's law. So there is one additional source of electric field, varying magnetic field in time. So number 4 equation, which we already considered, but worth repeating, that the same integral over closed path for magnetic vector times displacement vector ds in the scope of Amperes Maxwell law is equal to the product of permittivity of free space mu naught times conductivity current I plus product of epsilon naught permittivity, electrical permittivity times magnetic permittivity of free space times first derivative over time of electric field flux. So now we show with this equation that there are two sources of magnetic field. So we already discussed two sources of electric field with equation 1 and 2, which stands for electric charge and varying in time magnetic field. Equation 2 doesn't give us any sources of magnetic field because this integral, like magnetic field flux over closed surface, is equal to 0 always. But equation 4 provides us with two sources of magnetic field. So first is conductivity current, and second is varying electric field in time. So the same way as conductivity current as mobile electric charges, because conductivity current is defined by moving electric charges in space. Along to this option, we also can create magnetic field with varying in time electric field, which is associated with this first derivative of electric field flux over time. And in order to describe also not only the electromagnetic field itself, but also its possible interactions with electric charges, which are placed in this space where electromagnetic field exists, we add one more equation, which tells us, which is considered as Lorentz law, and provides us information about total force which is exerted on electric charge and consists of two components. First one is electric force, and second is magnetic force. So taking this all into account, we can describe any electromagnetic fields and its interaction with electric charges placed into this electromagnetic field. So now our next step, which we will focus during our next discussion, will be the calculation of speed of spreading of electromagnetic wave in free space by combining this Maxwell equation. So that we will do in free space, means not just vacuum, means the electric constant of unity, but also we need to highlight that this is a free space of any charges. So in our consideration, electric charge will be equal to 0. And also, if there are no charges, there should be also no conductivity current, because conductivity current is always associated with mobile charges, so they need to exist in the space which we consider in order to contribute to conductivity current. So electric charge and conductivity current will be considered as equal to 0. And based on this, we will show that speed of electromagnetic wave is equal to speed of light, which was experimentally measured. So that is very important statement, because it shows a fundamental evidence that light is a form of electromagnetic radiation. And also would be good to highlight that Hertz also made very important experimental observation in generating and detecting electromagnetic waves. So it was a proof, experimental proof of this theory developed by Maxwell, in particular introducing displacement current. So if I share with you my screen again. So if we consider this right part of the slide and have some induction coil and capacitor LC, so-called LC circuit, which can be a source of oscillations in current, because we transform initially energy accumulated in capacitor in form of electric field into energy accumulated in the inductor in the form of magnetic field, and that happens back and forth quite many times, because let's say the resistance of such a circuit is very small. So this oscillating current in such circuit creates electromagnetic field. So why? Because we have a combination here of varying in time conductivity current and also varying in time electric field, which is concentrated between the plates of the capacitor. So we, by realizing this current and electric magnetic field oscillations in the inductor capacitor circuit, create electromagnetic waves. So that shows that indeed varying in time electric field and conductivity current can create electromagnetic fields. So we can form them, but initially we didn't know for sure. But with Hertz experiments, which he carried out by detecting, building some receiver, which is also some conductor with a capacitor, which is tuned to receive these electromagnetic waves and transform them in oscillations of electric current in a new loop, which was under equilibrium previously. So these oscillations of electric current in the receiver, they are induced by absorbing electromagnetic wave. And then we show that varying electric and magnetic field, which is associated with the electromagnetic wave, that's what can spread in space, can also induce, like be considered as sources for conductivity current in the receiver, and also result in the same frequency as electromagnetic wave, oscillations of electric current and varying electric field in this capacitor. So that is kind of experimental evidence of the validity of those equations, Maxwell equations, which we discussed and which were theoretically predicted. This is really a great combination of theory and experiment, which work in a complementary way and support each other. So with this, I would like to finish our discussion. I would like to remind you that during this discussion, we introduced the concept of displacement current, which is associated with the time varying electric field flux. So then we can go from Amperes Law for Amperes Maxwell Law. And also we considered in details the combination of four very important equations, which stand for and considered as Maxwell system of equation, together with Lorentz law, which describes force exerted on electric charge in electromagnetic field. They describe whole electromagnetic field and like all information necessary about electromagnetic field and its interaction with electric charges. So our next step is to derive the speed of electromagnetic wave, electromagnetic field propagation in free space, assuming that total electric charge and electric current in this space is equal to 0. So if you have any questions, you're welcome. So then, thank you very much for your attention, and see you next time on Wednesday when we continue our discussion. Take care. Have a good evening.
Goodbye.
Bye-bye.